Okay, so welcome everybody to today's session in String Math 2021. It's a pleasure to introduce Lotte Hollands from the Heriot-Watt University. And yes, I would like to give I should have noted the title. I'm sorry, it's on my screen somewhere.
That's fine.
I give the floor to you.
Yeah, so thank you very much for that introduction. And thank you very much for the invitation, of course. So the title of this talk is Exact WKB and Abilenization for a particular linear differential equation of degree 3, which we called the T3 equation in this paper that appeared a while ago with Andy Nijtske. So in this talk, I will start off with a little bit of motivation, why we would be interested in any of the 3 keywords in this title. I will then have a look at a more familiar example, the Mathieu equation, which has been studied in depth. And last, I will continue to the key example of this talk, the T3 equation. Right, so why are we interested in this particular T3 equation? Well, as you probably agree, there are many well-known differential equations in mathematical physics, and some of them, they appear as Schrödinger equations. Think of the Schrödinger equation for the quantum harmonic oscillator, which is just given by a degree 2 equation with a quadratic potential. A slightly more generalized version of that is the Mathieu equation, which is a Schrödinger equation with a periodic potential. And yet another example, maybe a bit mathematical nature, of a bit more mathematical nature, is the Gauss-Hyper geometric equation, which is a prototype of a Fuchsian differential equation on the 3-punctured sphere. So that means it has 3 regular singularities at c is equal to 0, 1, and infinity. So just like this hypergeometric equation, any Schrödinger equation may be complexified and given a global meaning on a Riemann surface C. These global operators, they're sometimes called opers. And these differential equations, they feature prominently in the Bethe-Gauge correspondence. And I'm particularly interested in the 4-dimensional version of that correspondence as formulated in that paper by Nekrasov and Chatashvili. So this is a correspondence between the 4-dimensional n equals 2 theory in the so-called, in a certain background, which is called the half omega background, and a quantum integrable system. So I guess the main example of this correspondence is if you consider a very well-known field theory, namely the n equals 2 pure Young-Mills theory. And if you consider it not on R4, but on a slightly deformed version of R4, which I call R2 h bar times R2, where the h bar is a parameter that corresponds to an isometry of this 2-plane. And this Young-Mills theory is very well known for a long time to be dual to a certain integrable system. Namely, in this case, it has the form of a periodic Toda chain. That means you're considering k particles on a real line which are interacting through this potential here. So the statement of Nekrasov and Chatashvili is that if you consider this Young-Mills theory in this half omega background, then you get a quantized periodic Toda chain. And in this case, that will be described by a Mathieu equation that we will meet a bit later on. So more generally, these integrable systems, I should say, they are of Hitchin type. And these operators, with parameters h bar and e, they may be seen as quantum Hamiltonians of this Hitchin system, which is based on the surface C. So let's go back to the three examples that we started out with, these three Schrödinger equations. So starting out with the harmonic oscillator. So if you complexify that equation, it will be a differential equation on the plane, on the complex plane, with an irregular singularity at infinity. And in physics, this would correspond to just a free hypermultiplet. So just the theory of a free hypermultiplet, which is sometimes also called the 82 theory. So the spectral curve or the Seiberg-Witten curve for this theory, you can find it by looking at the semi-classical approximation of this differential equation, and then it gives a degree 2 cover over this complex plane. The Mathieu equation, on the other hand, if you complexify that equation, it becomes a differential equation on the twice punctured sphere. It corresponds in physics to the pure SU2-Young-Mills theory, and its spectral curve or Seiberg-Witten curve is a punctured torus. The last example is the hypergeometric equation. So I'm giving this example because it's really a rank k is equal to 2 version of the T3 equation that we will see next. So in terms of physics, this is an elementary block from which you can build any superconformal theory of class S of type A1. It has a Lagrangian description. It corresponds to 8 half hypermultiplets. And its underlying curve, as we saw, is this 3-punctured sphere. So most of these differential equations, they have been studied in depth. So we know their eigenfunctions, monodromies, spectral problems really well. So in this picture on the right-hand side, you see, for instance, a picture of the bands and the width of the Mathieu equation. And so often these results of these studies, they can be phrased in terms of special functions, such as parabolic cylinder function, Mathieu functions, hypergeometric functions in our examples. So from the n=2 field theory perspective, it is kind of obvious how to generalize that story to higher ranks, so k bigger than 2. But it is also very clear that we will meet new difficulties, because the field theories that correspond to these higher rank differential equations, they will be intrinsically strongly coupled, which means that you can't study them with the usual Lagrangian methods. And at the same time, much less is known about special functions for higher rank cases. So my favorite example of a higher rank equation is this equation, the T3 equation. So as it's given here. So this equation is a linear differential equation of order 3. So it's determined in terms of two functions, P2 and P3, where P2 is just a function of C and H bar, and P3 is proportional to a complex parameter U. And you might obtain this differential equation by writing down the most general Fuchsian differential equation on the 3-punctured sphere. So that means it has regular punctures. It has regular punctures at these 3 points, which are also known as maximal punctures in physics. And then what you want to do is you want to take the residues at all the punctures to 0, so that the monodromies around the punctures will be unipotent. So this seems to be a very fundamental, elementary, I guess, example of a third order differential equation. But almost nothing is known about it. Seems to be known about it. There are no special functions. The monodromies are not known. All in contrast to this k = 2 equation, the hypergeometric equation. So I should say that there is a generalization of hypergeometric equations to higher rank, generalized hypergeometric equations, but these are not differential equations on this three-punctured sphere with three regular punctures, with three maximal punctures. So they involve some other constraint on these residues at the punctures. So in physics terminology, they will correspond to two maximal and one minimal puncture. Right, so the theory, the field theory corresponding to this differential equation, to the T3 equation, is the so-called T3 theory. This is the basic building block in constructing superconformal field theories of class S of type A2. And by Giotto, this theory is identified as the so-called Minahan-Nemeshansky theory with flavor symmetry E6. So you might wonder where this E6 comes from. Turns out that all these, the three punctures on the three-punctured sphere, they correspond to an SU3 flavor symmetry group. And you can argue that in the infrared, that this flavor symmetry group is enhanced to E6. So while we do not know much about the microscopic definition of this theory, we do know quite a bit about its low energy description. So for instance, we know what the Seiberg-Witten geometry is. So the Seiberg-Witten curve in this case is a puncture torus, which is covering the punctured sphere. And it's given by this equation of order 3. So in this form that I've written it here, the canonical 1 form or Seiberg-Witten form has this natural form. So notice that phi2, the quadratic differential, is just equal to 0 for this theory, and phi3 is proportional to the complex parameter u, which is the Coulomb parameter of this theory. So this theory has a one-dimensional Coulomb branch. Right, so why would we be interested in exact WKB, the second keyword of the title? So exact WKB is a method for studying mononormies, or in general Stokes phenomena, vectors of differential equation. And so there are some applications that we will be interested in this talk, and one of them is suppose that we want to solve a spectral problem. So suppose that we have a differential equation of this type, and we restrict the argument of h bar to be equal to theta. So we fix the phase, and so then the spectral problem is given by looking for solutions E such that this differential equation holds where phi of C is restricted to a particular class of solutions. So an example is when D is the Schrödinger equation for the harmonic oscillator. So in that case, we would restrict our functions psi of C to be L2 functions. So they go to 0, the asymptote to 0 at infinity. And if we solve the spectral problem, we find the spectrum, the discrete spectrum of this quantum harmonic oscillator. So more generally, these spectral problems corresponding to to any kind of differential equation, a higher rank Schrödinger equation, they would correspond to, they would give a meaning to what you would mean by quantizing the Hitchin system based on the curve C. So central to the WKB method is looking for local solutions which have a particular form. They are of this exponential form, where the one form lambda theta can be approximated as a series expansion in the parameter h bar. So the statement of so the statement is of exact WKB is that these differentials lambda theta, that they can actually be found in an exact form, and that they will have an asymptotic expansion in terms of h bar. when h bar goes to 0 in a certain half plane, which is centered around theta. So once you find these local solutions, you can extract the so-called quantum periods, which are sometimes called Rho periods, which are really period integrals of this one form lambda theta over a one cycle in the spectral curve sigma. So one application that I want to mention of these quantum periods is that once you've defined these quantum periods, you can extract a partition function, a certain partition function, which well, I've denoted by W tilde here. But yeah, I don't have much time to say about that in this talk, but I will rather refer to an upcoming paper for that. So why are we interested in abilenization? Well, it turns out that abilenization leads to a new geometric reformalization of the exact WKB method, which works for all k. And the key to this abilenization method is to view the operator D as a flat SLK, C connection on C. So once we have we see this as a flat connection, and the abilenization method would produce a flat C star connection on the cover sigma. And then these exact quantum periods, which play such an important role in the exact WKB method, they will just be equal to the holonomies of this C star connection on sigma. So as we've seen, exact WKB as well as abilenization, they depend on this phase theta. And this phase that corresponds to a choice of spectral network, or in the context of exact WKB, it's called a Stokes graph. And I will say a little bit more about what that means later. But what I want to say now is that if you keep this theta fixed, then these quantum periods, they can be extended to coordinates on the modular space of flat connections on C. And these coordinates, they are sometimes called spectral coordinates. Right, so the aim of this talk will be to work out abilenization and exact WKB for the T3 equation. And that turns out to be a rather cool example with some new features. And the second aim will be to formulate a new spectral problem for the T3 equation. And so in other words, that means we formulate what one could mean by quantizing this particular Hitchin system, which is based on the three-punctured sphere. Right, so before we go there, I want to review a more familiar example. So that is the material equation. So this Schrödinger equation with a periodic potential cosine of x. So if we can complexify this equation by introducing a new variable, c is e to the power ix. And then this equation turns out into this degree 2 differential equation in terms of the function P2 of C. And you can immediately see that this function has this function has singularities at C is equal to 0 and C is equal to infinity. So in other words, this will define a flat opal connection on the complex sphere with irregular singularities at C is equal to 0 and C is equal to infinity. So again, as we've seen in the beginning of the talk, the semi-classical limit of this opal will be the spectral geometry as shown on the right. Right, so exact WKB depends on a choice of phase, theta. And that phase theta was equivalent to choosing a spectral network. So what is a spectral network? So a spectral network is a collection of trajectories on C. So it's made out of trajectories which all emanate from the branch points of this covering. And these trajectories have to satisfy this constraint, namely if they have to satisfy that e to the power minus I theta times the integral of the one form lambda must be real. So in the case of the Mathieu equation, there are two interesting, at least for this talk, interesting spectral networks, two interesting isotopy classes, I should say, of spectral networks. And one of them appears when the energy E is negative and it's smaller than -1, and when the phase is equal to 0. So in that case, if you start drawing the spectral network, so it's made out of trajectories, starting from these branch points, particularly these two branch points which I've marked here. And these trajectories, they will go into, in general, into 3 directions. So there's one going all around the circle and one going back all around the circle. So since these two trajectories are intersecting, are overlapping, it's a bit of a special kind of spectral network. It's a non-generic kind of spectral network. There are some other trajectories that start out from the other branch point. One is going into the puncture at c is equal to 0, and the other ones are again going around the loop. Was that a question? No. Okay. So these trajectories, they are labeled by 1, 2 or 2, 1, and this depends on whether this quantity e to the power minus I theta integral of lambda, whether it's positive or whether it's negative. So well, actually, so in this spectral network on the left, I've drawn 2 other cycles in green and in red. So these are the 2 1 cycles corresponding to a choice of A and B cycles on the spectral cover, which in this case was the punctured torus. So the other interesting isotopy class of spectral networks, it appears, for instance, when the energy is greater than 1 and when the phase theta is equal to 0. And it's slightly different in the sense that in this case, there is this trajectory. Well, there are these 2 trajectories which overlap in between the branch points. So I will call the network on the left side W and on the right side W tilde in the following. Right, so suppose that we want to abelianize the Mathieu equation. So what does abilenization mean? So abilenization starts out with a flat connection, which I've denoted by number here. And it starts out with a spectral network on a curve C. So what it means to abelianize is really to find a gauge such that this flat connection is diagonal on the cells which are determined by the spectral network. And so, for instance, in this particular cell, the diagonalization of lambda is characterized by a basis of local sections Si, Sj. And moreover, we require this gauge to be such that if you cross a trajectory, then the corresponding gauge transformation is unipotent. So if it's a trajectory of type 1, 2, then it has a non-zero entry at the position 2, 1, and the other way around for a trajectory of type 2, 1. So if we find such a gauge with these properties, then the statement is that we may lift this flat connection to a C star connection on sigma, on the spectral curve sigma. So the exact WKB method, it's really a special instance of this. It provides one particular W abelianization if this connection nabla is an open connection, and if the spectral network is the Stokes graph for this particular phase theta. In that case, the local sections SI, they are given by the local WKB solution, so that is, they can be approximated by a formal WKB in a formal WKB expansion, as is here. And the exact sections can be found by then Borel resumming these formal expansions along array with phase theta. So suppose that we want to do this for this Frenkel-Nielsen network that we met, the network that I called W. In that case, so suppose that we want to abelianize the OPER corresponding to the Mathieu equation for a phase which is given by 0. So that's exactly when we find this network. In that case, so abelianization tells us that we have to find a particular gauge. A gauge which is characterized according, well, at least for WKB abelianization is characterized by solutions, local WKB solutions. So in this case, I've denoted all the basis elements, all the basis of local sections in the picture on the right. So for instance, the one that I've highlighted is a basis of local sections near the puncture at c is equal to 0. And these would be solutions to the Mathieu equation that exponentially decay if you walk along this trajectory towards c is equal to 0. So the local basis of solutions, for instance, in this cell, which are near the puncture at c is equal to infinity, they are similarly characterized as solutions that exponentially decay if you walk along this trajectory towards infinity. And so the other solutions that we need are the solutions in this intermediate region. So these are going to be eigenvectors of the monodromy of this Mathieu equation around c is equal to 0. So the claim is that if you choose the basis of sections as in this figure, then that will provide you an abelianization. And then that defines a C star connection on the cover, on the spectral cover. And then we can read off the exact quantum periods, just as the holonomies of the resulting C star connection. So in this example, you can really compute that through. And what you find is that, for instance, the spectral coordinate, which is labeled by the A cycle, it's given by a monodromy, by an eigenvalue of this monodromy M. Whereas the spectral coordinate corresponding to the B cycle, it is a ratio of Wronskians of these solutions, psi I and psi I prime and psi I double prime. So as I've noticed before, so we can analytically continue these quantum periods then to coordinates over over the whole moduli space of flat connections. Right, so the application that I want to discuss, it's sometimes called a spectral problem of type A. This spectral problem comes up when we choose C to be equal to e to the power minus x prime, where x prime is real. So that turns this complexified Mathieu equation into the so-called modified Mathieu equation, which instead of a periodic potential now has a Quash potential. So it's more like the harmonic oscillator. And in this case, there is a standard bound state problem, which is associated to this equation. And that is look for, well, just like the harmonic oscillator, that's look for energies E such that there exists an L2 solution to this equation. If we translate that problem in terms of our spectral coordinates, it just says that xb is equal to 1 because having, maybe I should choose another color here, because so if we consider this problem, we're really looking at solutions along this axis, and so that means that we're looking for L2 solutions. So we're looking for solutions that are decaying at either end. So that means that we want psi1 and psi1 double, psi1 and psi prime, 1 prime, to be proportional, which means then that that the spectral coordinate xb, that it just reduces to 1. So in terms of our spectral problem, in terms of our spectral coordinates, the spectral problem has a very simple form, and this is sometimes called the exact quantization condition for this problem. So using WKB, the WKB approximation, we can now approximate what that means for the energies, and you will find a constraint of this type. So one check of this is that, so the energies that you find will all be smaller than -1. They will be real and smaller than -1. And that means that we can really use the exact WKB, the coordinates that we computed with respect to the spectral network that was defined for E smaller than -1. So there is another famous problem, which is sometimes called of type B, and that spectral problem is formulated in terms of the original material equation with periodic potential. And so here we have to, so this spectral problem is formulated slightly differently. So here we want to look for energies E such that there exist anti-periodic solutions. So you could generalize this to quasi-periodic solutions, but I've chosen this as a simple example here. In terms of the previous spectral coordinates, that would really mean that XA is restricted to 1. However, because XA were really the eigenvalues of the monodromy, and this minus sign is some artifact of some square roots. In any case, so since all the energies that are solutions to the spectral problem are larger than -1, it actually turns out that although this is a nice condition, we cannot use the WKB approximation to make any nice statements about this condition. We cannot use WKB to find approximations to the energies. To do that, we need to look at this other spectral network, W tilde, which was defined for energies larger than 1, actually. So if we do that, so similarly as before, we find an abelianization with respect to that particular spectral network. We find the spectral coordinates, which in this case have a slightly different form, as it's written here. So XA tilde and XJ tilde. And so now we can use exact WKB to say anything about this spectral problem, namely the new exact quantization condition in terms of these coordinates will read as in this formula. And in particular, so we can use WKB for these XAs and XBs to get approximations for the energies. And this extra factor, the square root of 1 minus X tilde of B, that explains the gaps that you find in the material spectrum, if that if that means anything to you. But so the point is that if you're being careful in applying this abelianization method or in using exact WKB, you can even find new sort of things in very old problems, because this exact quantization condition, we haven't been able to trace it back in the literature. Right, so to take away, so exact WKB can be formulated geometrically in terms of abelianization. So for every spectral network, one obtains holomorphic Darboux coordinates on this modular space of flat connections. And these coordinates, they will be the sort of more well-known Varro symbols when you evaluate them on these Oper connections or on differential operators with the correct phase. Right, so let's see, can I say a little bit about this? Yeah, so let me say a little bit about this diagram on the right. So, so I defined, well, I showed you two spectral networks, W and W tilde, and I showed that one appeared on the negative real axis and one on the positive real axis. It actually turns out that if you just look at the negative real axis, so if you look at E being smaller than -1, then you can also recover the spectral network W tilde, but at a different phase. So it would appear here at this phase theta is equal to half. Yes, right. So yeah, so just a small remark. You can then, so once you've got these holomorphic, so they're so what you find in this picture is so this is a picture of all the active rays. So that means that if you look at the spectral networks, at how they change, as if you change the phase theta, then you'll find a new isotopy class of spectral network whenever you see an arrow in this picture. So to any sort of isotopy class of such spectral network, you find a new kind of holomorphic Darboux coordinates. And so for any choice of holomorphic Darboux coordinates, you can define a generating function as in these equations. And this generating function, it happens to have a nice physical interpretation. In particular, when the phase is equal to 0, then it happens to agree with the Nekrasov-Shatashvili superpotential, which has also appeared, I think, in Alda's talk yesterday. Right, so let's go to my favorite example, the T3 equation. So remember that this was the this linear differential equation of degree 3 on the 3-punctured sphere, which was characterized in terms of these terms P2 and P3. So you might note that this differential equation really only depends on the ratio of U over H bar cubed, which makes the analysis a bit more simple, or at least to explain. Right, so in this case, if we want to do abelianization, if we want to abelianize this T3 equation, we're interested again in the corresponding spectral networks, because we have to choose a certain phase theta. And these spectral networks in this case are actually much more complicated than what you would see in the A1 case, in the case equal to 2 case. In particular, if theta is generic, then you find that these networks are wild. So that is, they are dense, at least in a region of C. And then there are special phases which are labeled by integers P and Q, which are co-prime. And for these special phases, you'll find that the network is compact, just like this Frenkel-Nielsen network W that we encountered before. So all of the trajectories are really double trajectories. So some examples of this. So if theta is equal to 0, then so the networks, they really increase in difficulty when you make P and Q larger. So the simplest one you can find for P, Q is equal 1, 0. And it's this circular network. So we have, so in this case, turns out actually that the cover, the spectral cover is not ramified. So the branch points, they overlap the punctures. And so there are double trajectories, which are now labeled by either 1, 2, 2, 3, or 3, 2. And so if you increase the values of these integers, then you will get more and more complex networks. So we will restrict this in this talk to the simplest network, this circular network. And so we want to study abelianization for the simplest network. So that means, so pick any generic SL3 flat connection with unipotent monodromies. And suppose that A, B, and C, as in this figure, they are the monodromies around these cycles, going around the punctures. So let us now suppose that we can find such an abelianization, and let us call the basis of local sections in this middle cell by psi1, psi2, and psi3. Then all the requirements for this to find an abelianization, they determine what the basis would be in all the other cells. So this is the basis in the original cell, and all these other bases, they are determined by the constraints that we impose on being an abelianization. And there is one additional, there's one additional set of constraints which are given on the right, namely. Let me perhaps see this a bit more clearly. So suppose that we, for instance, consider the gauge transformations across this particular trajectory, then they need to be of a unipotent type for a single trajectory. Since we have a double trajectory here, we get a composition of two unipotent matrices, and those imply that these two basis factors, B inverse times psi2 and C times psi1, that they should be in the span of these two basis factors here. So that's how we arrive at this set of constraints given by star. So now we say that this original basis that we chose, that is we say that it is in a special position if star holds. And so what this implies is that all the W abelianizations for this network, they are in one-to-one correspondence with such bases in special position. And it turns out, well, scaling these bases doesn't make a difference. So really, they're in one-to-one correspondence with projective bases. Right, so that's nice, but how do we characterize these special bases? I mean, how many are there even? So here comes in a bit of linear algebra magic. So what we can do is we can define a map from a map phi hat from CP2 to CP2, and it's a composition of 3 maps, and one of these maps, phi b, c, it is defined by so starting out with just any basis with an element psi1, and by mapping that to the plane, which in projective space is a line, which is spanned by psi1 and psi c times psi1, and then intersecting it with a plane in projective space, which is spanned by b times psi1 and bc times psi1. If you look at this carefully, then you'll find that if psi1, psi2, and psi3 were a special basis, then the intersection will be the element psi2 of the special basis. And so if you look at the composition of all of these three maps, then you'll find that the fixed points of this map correspond to the special basis. Right, so this reformulates it again a little bit, but still we don't know that much more. So what turns out, and what turns out to help us a lot, is that I had this map from CP2 to CP2. It really preserves a one parameter family of cubic curves, and these cubic curves are parameterized by a parameter t, and they're defined in terms of the Wronskins of these basis elements psi. So this one parameter family of cubic curves, it's actually supported at 3 base points, which lie on a line, which is equal to one of these elements in this family for a particular value of t. So now what we can do is we can blow up these base points twice to get a smooth rational elliptic surface, and it then turns out that this has 5 singular fibers, one fiber of Kodaira type 4 star, which corresponds to this line L, and then in general there are 4 more simple fibers of Kodaira type I1. So this is kind of interesting because now we found that now we can actually count them. So we know that the abilenizations correspond to the fixed points, to the nodal points of this rational elliptic surface. So it turns out that there are actually 4 plus, well, a line of abilinization. So these all these I1 fibers, they just contribute the node, but the 4 star fiber contributes a whole line of the line L of abilenization. So we find that for this unipotent problem, there are 4 plus infinity abilenizations. You could also do this for the semi-simple case, where you do turn on all the masses, and then you find that there are actually 12 discrete abilenizations. So whereas there are 4 discrete abilenizations, only one of them corresponds to the exact WKB one, and that's the one where XA is approximated by the WKB approximation. So now that we have this, we can do all the numerics, and we can plot the spectral coordinates corresponding to all of these abilenizations. And so that's what you see in this figure, and you'll see that one of these abilenizations indeed follows the line given by the WKB approximation. So maybe as a reference, the spectral coordinates in this case, at least XA is given by this ratio of, but this particular ratio of Wronskins, and XB is given by a more complicated ratio of Wronskins. That's all in the paper. So maybe what's even more interesting is that these 4 discrete abilenizations, they have quite an interesting analytic structure over the U prime plane. So as I said, you can analytically continue them to any T3 to any T3 OPER. So what turns out is that if you look at large U, and that is what this figure represents, then this monodermy agrees with what you would expect from WKB. It agrees with the periods, the classical period C gamma. But if you look at small U prime, then you find something different, namely than what you would expect from the WKB approximation. Namely, you find that there are 2 special points in this U prime plane around which there is an order 2 monodermy. And together they build up the order 3 monodermy that you would expect from WKB. So this is something which might slightly remind you about cyber-Witten theory. So you might wonder whether you could define a global quantum corrected period, C tilde, and what its interpretation is in physics. So unfortunately, these are questions that I cannot answer yet. Right, so since time is almost up, I want to say one more thing, and that's that this abelianization defines a new spectral problem. Well, this is what we were looking for as well. So the spectral problem is a bit of a different type than the ones that we've used before, because we're not just talking about a Schrödinger equation. We have an order 3 differential equation on this 3-punctured sphere. And but similarly as before, we might interpret this equation xa is equal to 1 as an exact quantization problem for a certain spectral problem. So it turns out that this spectral problem is given by, so you want to find the solutions which, the solutions U prime for the T3 equation, for which the solutions are such that the monotomies satisfy this. One of these two equations, and again, then you find you can find numerically you can find solutions to these equations, and in this case you can also approximate them with WKB. Right. So this is sort of an interpretation of what it would mean to quantize the Hitchin system corresponding to this particular curve. Right, so maybe the conclusion. So I hope you agree that this T3 equation is very rich with plenty of hidden structure. It's really, I mean, this talk is really an invitation to learn more about this, what seems to be, to me at least, quite a fundamental equation. So reformulation of exact WKB in terms of abilenization uncovers some of this structure. So we would only see the structure of these 12 abilenizations, or 4 plus infinity, by looking through the lens of abilenization. Moreover, abilenization is not unique. So whereas in actually, well, most of the cases, at least, well, I think all of the cases that have been previously considered, you can find a certain framing or so to make abilenization unique, even if you thought it might not be. In this case, it's really, I mean, it's very tricky, or maybe not possible to define such. You really find that these abilenizations, they correspond to the nodes of a rational elliptic surface. That seems to be the main underlying message. And so there are some applications that we've seen of this. So new spectral problems, and new spectral coordinates, and novel n=2 partition functions, because it is not known at the moment what we would mean by these effective superpotentials for this particular intrinsically strongly coupled E6 theory. So I think that's it.
So let's thank Lotte Hollands for this beautiful talk. So are there any questions? Okay, I see that Greg Moore has raised his hand.
I love it. Could you say a little more conceptually what you mean by saying the abelianization is not unique? It looks like you found this in this this very non-trivial example.
Uh-huh.
I'm wondering if it's possible. I'm trying to understand what you mean by the abelianization is not unique. I mean,
yeah. So if we
suppose we have a spectral network.
Uh-huh. Yes.
Then there's kind of a prescription for.
Yeah, you can also
we can look at the roots, right? You know, each of the branches corresponds to one of the lambdas.
Uh-huh.
Integrating that lambda. Are you talking about some kind of non-uniqueness about how we define the transition functions across the spectral network? Or I don't really understand this non.
So what I'm saying is that there are a number of solutions to the abilenization problem. So that well, if we let's see. here. Well, it's a bit disturbed, but if we look at this figure, then I say that there is a number of solutions to this abelianization problem. That is, there is a number of bases psi1, psi2, and psi3, which all have the nice properties that that they diagonalize this connection nabla in the cells, and that they have the required unipotent properties when you cross these trajectories. You can also
is this a discrete infinity or a continuous infinity, or? So
as I said, for the unipotent case, it's 4 plus 4 discrete plus a continuous infinity, and for the semi-simple case, it's 12 discrete solutions.
And then there's a non-abelianization map where you push back forward. I mean,
that's right. Yeah, that's right. So,
are they going to give different flat connections if you push back?
So let me see. So the non-abelianization is a bit different. So in that case, I think there are 2 solutions. Well, I have to remember this. So there. Okay. So in non-abelianization, you would write these unipotent matrices in terms of the information of the abelian connection, and you would find that there are 2 or 3 different possibilities, I think. Right. So some of these abelianizations they can be matched with one of the non-abelianization maps, and some of the other can be mapped with the other one. So there's one non-abelianization solution which has sort of the nice WKB properties. So that is the one that you use to compute BPS states. And that is the one which also on the abelianization side corresponds to the WKB one.
So, right, good point. So I thought the parallel transport with respect to the non-abelianization map would calculate the framed BPS states. So this kind of ambiguity you're talking about troubles me, because there should be an answer for the, right? I mean, if we
So
specify an interface, a path, then the parallel transport of the flat connection expansion in terms of the parallel transports of the abelianization with the coefficients which are given by the framed BPS states.
Yes, yeah. So
there should be a unique answer to that, right?
I think could it be that just these sectors that you're showing in this picture, that you have ambiguity of choosing how to filter your system. You have a system, your connection, vector bundle with a connection. What you're doing is you're splitting it right into line bundles, but actually maybe what you should be doing is splitting it by choosing filtrations which are transverse. And so if you think from that point of view, then there is a canonical way to choose these filtrations, and that would give you canonical decompositions. Those filtrations are given by growth rates. But of course, you could choose different filtrations. You could, if you have some way of choosing the basis to begin with, then you can use it to filter your system in a variety of ways. And maybe that's the ambiguity that you're seeing.
So you're not talking about filtrations at the punctures, but at filtration of the basis.
Well, it's just filtration given by a basis is just a way of ordering a basis.
Okay, I see. Yeah.
Right.
I'm not sure. I think this ordering.
But I mean, the filtration's defined by growth rates. The growth rates would be at a particular point, right?
Because they are. I mean, these are all flat things, right? So you then just parallel transport them too, and because you have cells, because you've chosen the spectral network.
Maybe we can move this discussion to the break in between, because the next talk is going to be soon, and maybe somebody else would like to ask a question as well. We'll have a longer break after the next talk.
Right.
Is there anybody else who would like to ask a question? All right. Well, if not, then let's thank Lotte Hollands again. And we resume in a couple of minutes. Should we just take a 3-minute break and resume at 36, whatever the thing before the, whatever hours you have in your time zone?